So just as a reminder where we ended, we talked about KAs a whole bunch, and then we went through and said we could also look at a KB. Similar to a KA, it's just the equilibrium expression. So we'd be looking at K equals your products over your reactants. Remember, the water won't show up because the water is officially a liquid, and its concentration is not going to change through the course of the reaction, so that gets folded back into our K. So that gives us our K expression. This one becomes different from the Ka because what we're now talking about is the presence of hydroxide ion. Since hydroxide ion was something that was fairly characteristic for our bases when looking at solutions in water, we give a special name to this one as well, and you'll get a Kb. The Kb, just like the Ka, can be converted into a pKb, and it's going to have the exact same connections that you would have seen with the Ka. So you can tie it back to Ka through the Kw, and you'll get this strength relationship. So the larger your Kb, the smaller the pKb, and the stronger the base. So all of those things tie in. What makes this challenging is since we're now looking at the base as opposed to the acid, is that it's very easy to get the two confused with each other, or also because of the interplay between them. So you just got to make sure that you're labeling really, really carefully and you're paying attention to what relationships you're looking at any given instant. Okay? Deciding which one to go through and use is going to have a lot to do with the presence of hydroxide or H3O+. If you're saying hydroxide, you're going to want to look at a Kb. They may give you a Ka, but you want to look at a Kb. So how can you convert that Ka into the Kb? If you don't remember, that's okay. Ka times Kb equals the Kw. Okay. So if you're forced into that situation where they're giving you the wrong K value, you can go through and convert it to the K value you actually want to look at by taking advantage of your Kw. Okay. And if you don't have that equation memorized, that could be something for your cheat sheet. Theoretically, it's also on the front of your quiz. Okay. So, which is the stronger base? Which solution would have a higher pH? So blue box at your tables. I think everybody is sick this week, which we'll discover later in lab. So we really only have 3 tables that can talk to each other? So talk to each other at your tables, or just sit and stew on it for a second. Cool, so we can come back to it. This is really just summarizing what was just on that last slide. So which one's going to be the stronger base? I thought you all just talked about it. Which one's the stronger base? Ammonia. Okay, why? Smaller pKb. The follow-up question is which one would have a higher pH? That's too easy. Which one has a lower pH? Well, if you knew which one had the higher pH, which one's going to have the lower? All right. Why hypochlorite? It's a weaker base. So we know the other one is producing more hydroxide ions, therefore going to have a higher pH. If we flip that up in the lower, that could mess with us. Okay, what else could we do to potentially mess with your brains? Which one has the lower pOH? Ammonia, the lower pOH, you're now looking at the concentration of hydroxide ions. A lower value on that P scale is stronger, okay, or is more concentrated. So we're looking at a lower pOH, you're going back to the stronger base, ammonia. Kind of make sense? Okay. Do you get kind of the feeling how we could ask all sorts of questions that are going to cause real subtle changes to your interpretation? Right? It's going to require real careful monitoring of both what is given and what you know as far as your interpretation and make sure you keep them straight. Questions? Okay. So conjugate acid-base pairs, we still get this system popping up again. Okay, while we could reference the water as conjugate partners, water can be pretty much both, so it's kind of boring to reference water as your conjugate partners. So instead, what you're typically referencing is the non-water things. Okay? So HCN is your acid. Okay? When mixed with water, it's going to produce H3O plus and the conjugate base, H2O. Okay? If we took the conjugate base, cyanide, and put that into water, what's going to happen? It's going to produce HCN and hydroxide. So the reversibility in these reactions gets a little bit strange with how we're going through and interpreting. Okay, the net is going to come out the same, but we're going to reference Kas and Kbs slightly differently for those forwards and technically backwards reactions. Okay. For your acid-base pair, we just talked about your Ka times your Kb will equal 10 to the minus 14, which is also known as the Kw. Okay. If you were given the pKa's, you could then go through and equate that through on the 14 scale. Kind of, sort of? Okay. So, relationships between all of our K's. We've got a table here. We want to start filling in that table using the relationships below. As you go through and fill it in, try and identify which is the stronger acid and which is the stronger base. Same deal, blue box. Start working and putting some stuff together. This does involve a calculator, theoretically. So for the sake of the recording, how are we calculating the pKa's? What are we doing?
Negative log.
You're just taking the negative log of the Ka, which came from over here. How are we getting the Kb's?
KW.
Right, so there's a couple different ways you could go through and do it, but it sounds like what most people were doing for the K, is solving from that expression. Okay. Go ahead. Say that again, because that was useful.
I solved for KB before PKB.
Which is also fair. Yeah. Most people, I think, would solve for the KB first. Did anybody solve for the PKB first? Before KB? Okay. Could you solve for it first?
Yeah.
How?
Subtract the pKa. Yeah.
You also have that pKa expression. So there's a variety of ways that you could go through and you could nail down each of those individual columns. Kind of make sense? Mm-hmm. That's going to come down to whichever one you are comfortable with. It's up to you to kind of decide and navigate that system. All right. The last question, acid strength. Which one was the stronger acid? Why is formic acid the stronger acid? Smaller pKa, perfectly acceptable. Oh, sorry, you lost the pKa. Why is formic acid a stronger acid?
Larger K.
You have that larger Ka expression. Does that make sense? So you can go from either of those spots. If you're given a Ka, you can just evaluate your acid strength from the Ka, or you could convert it to the pKa. Again, it's going to come down to wherever your comfort lies within that individual system. Okay. If we flip that and now look at the base, which one's the stronger base? The acetate comes in as the stronger base. Okay. Why? The smaller pKb. Kind of, sort of? Okay. So we could go through and look at fun coloring if we really wanted to. And then we could switch to a new question, which would have a lower pH at 1 molar solution of acetic acid or a 1 molar solution of formic acid? What do you guys think? What does lower pH mean? More acid, a higher concentration of H3O+, that's a 3. Okay. Which of those two is going to generate more H+? The stronger acid should generate more H+. Which one was the stronger acid? The formic acid. Kind of makes sense? Okay. Again, lower, higher, when you're dealing with pHs can be really wicked to deal with. Make sure you kind of convert those, or I would argue you should convert those out. That means more acid, a higher concentration of H3O+. You could even go through and say that that means a stronger acid. Okay. And if you really wanted to push on it, a stronger acid would have what for a Ka? Should be a bigger Ka. What should the pKa be? Okay. So all of those things are different interpretations, ultimately the same thing. You're just coming up with a different language to go through and represent it. Kind of make sense? So what's the concentration of H3O+ at equilibrium? If 0.02 molar acetic acid reacts with water, calculate the pH of the solution. Okay, it is a blue box. Should we just let you run with it? Yeah. Okay. Start putting something together to kind of work your way through it. First thing I'll actually ask, is all of that 0.02 molar acetic acid going to turn into H+? No, it's not a strong acid, which means you have to figure out how much converts across. Okay? In the grand scheme, how would we figure out how much was actually at equilibrium? What could be a useful way to note all of these changes? An equilibrium expression, so an equilibrium expression could be useful. So I'll go through and draw that. I'm going to end up writing it somewhere else. Do you know the CH3COO minus concentration? Do you know the H3O plus concentration? Do you know the concentration of CH3COOH? Okay. So if we're looking at that equilibrium expression, even that denominator, the CH3COOH, that's our acetic acid. We don't know that at equilibrium. We only know it initially. So we've got to come up with some system that allows us to decide how we could potentially change from our initial conditions to our equilibrium. There is a way that you could logistically organize that was discussed in the last unit very briefly, and it should be making a much larger appearance this unit. We'll let you guys work through it. Okay, there's a whole bunch of stuff written up on the board, but I really just had that conversation with one group. Would the class like that conversation? Yes. Okay, well then let's just delete everything. Okay. Well, don't worry, I'll just come back to it. I'm going to get rid of that picture because I need a little bit more space. Okay, and so the initial suggestion that came, I believe it was actually in the recording, was that we should write out our Ka expression, and officially our Ka. So our Ka is the concentration of our products, the CH3COO minus times our H3O plus, all over the concentration of our products. Okay, which is fine. Okay, and that is a perfectly great place to start until you get used to the patterns of what these questions are ultimately asking. And once you get used to the patterns that they're asking, you're going to immediately launch into something else. Okay? But let's start with our Ka. Okay? If we're going to figure out the concentration of H3O+, we would need to know the Ka. Do we know the Ka? Kind of, sort of, right? We're given the pKa, And we could convert the pKa into the Ka by doing what? The antilog, okay? So 10 to the negative 4.75. So that would get us our pKa. So that's useful. Do we know the concentration of H+? That hopefully would have been an easy answer of no, because that's what we're trying to solve for, right? We needed to know that. Okay, so we definitely don't know the concentration of that. Do we know the CH3COO minus? Nope, we have no context of what that is. Do we know the CH3COOH? Okay, and that's where we'll typically get a lot of people saying, well, yeah, that's 0.02. No, that 0.02 is where we started. That was our initial conditions. I had pure acetic acid, and then I dropped it into the water. The water then runs a very fast chemical reaction with acetic acid to go through and produce our products, our acetate and our H3O+. But to make those products, what happens to the concentration of the CH3OO minus, or CH3OOH, our acetic acid? To make products, what necessarily has to happen to that 0.02 molar of our acetic acid? It has to decrease. Right? Which means in solving our K expression, I know none of those systems except what the numerical value of Ka is. Right? That's 3 variables with 1 equation. That's going to be a bit tricky to go through and solve. Okay, so we'd have to go through and reason through some other things. If we look at our initial conditions, I guess we could show this in black because we knew this. Okay, what was the initial concentration of the acetic acid and acetate, the CH3COO minus, and our H3O+? It was 0. So what we can initially do is effectively solve for Q. This pulls back our last unit. What we're saying is that this is our starting point. We have 0 product. Does it make sense to have 0 product? Okay? As soon as I start that reaction, no, I'm going to start to form some of that product, which means that concentration has to go up. In the past unit, all you had to say was product concentration went up. Now we have to be a lot more specific. We have to say it goes up by. That's a lot more challenging. Right? But we can still leverage that information. Because we can go through and say that we know this is going to change. We're still evaluating our Q process. We know the acetate has to go up, the H3O+ has to go up, and the acetic acid has to go down. Okay, but by how much? And if you don't know, what should you say? A couple things. So one, I don't know. That's fair. Okay. How would we say that mathematically? Yeah, I just introduce a variable. Okay? So I'm going to say the acetic acid goes down by X, some unknown variable amount. If it goes down by X, what must happen to the acetate? Yes, it has to go up, but up by what? Why just an X amount and not 2X or 4X or 0.5X? Say that again. Yes. Yeah. What we're effectively doing is saying we have moles of the CH3COOH over liters of our solution. And what we're trying to do is convert into CH3COO minus moles, units are real cramped, liters of solution. Where's the conversion factor that allows me to get rid of moles of CH3COO? Of course, we picked the longest frickin' acid name possible. Where do I find that conversion? That's the mole ratio from our balanced chemical equation. So I can go up to that chemical equation and say, well, that's 1 and 1. Which then means how much does my acetate go up by? It's going to go up by the exact same value. Let's go with value. What's going to happen to the H3O+? The exact same value. Why? Because you're doing just a standard mole conversion from 151. That's all it is. Okay. What is going to happen? Okay, well, we know my concentration of the acetic acid is going to go down. Well, how's it going to go down? It's going to be 0.02 minus X. Okay. What's the acetate going to go up by? By plus X. The other one's going to go up by just X, right? Those values, whatever those numbers are representative for the solution at what point in time? Whenever I've achieved equilibrium. So those would be the equilibrium concentration. So remember what happens to the concentration of your species when you hit equilibrium. They're constant. They're fluctuating, but you're producing and forming at the exact same rates, producing and losing at the same rates, which means the concentration appears to be static. What can you now go through and do? Plug in your variables. Okay, so your pKa we said was 10 to the negative 4.5. I can't do that calculator in my head. The acetate was X times H plus, that's X squared over 0.02 minus X. What could we now go through and do? Solve for X. Right? Once we have X, what does that mean? Did somebody do it already? Is that a challenging one to solve for? Should I take that to mean yes? Because that would become 10 to the negative 4.5 times 0.02 minus 10 to the negative 4.5 times X equals X squared. We could group all our terms onto one side of the equation, and we would then have a quadratic to solve. How do you solve quadratics? A couple of fun ways to do that. Negative b plus or minus the square root of b squared minus 4ac over 2a. Thank you, because I didn't remember that part either. Okay, so you could go through and solve the quadratic. When you solve that quadratic, you're going to get two values for x. Okay, how do you know which one is correct? Okay, one option, it's got to be the positive value, because if it's the negative value, I'd have a negative value for x. That doesn't make any sense. Okay, what if they're both positive? Happens much less often. If they're both positive, go to this equilibrium concentration for our acetic acid, sub one value in. When you sub one of those values in, what do you end up with? A negative number. Could that possibly be the correct answer? No. So pick the other one. Okay? And that would then give you the correct x value. Okay? That's the painful, true mathematical logic that you have to run through all the way through with this. Right? Other options. Do you have a graphing calculator? Do you know how to use it? Maybe. You could plug in your quadratic expression, right, into your calculator and look at a plot wherever it's crossing, what is it, the x-axis? You now have your values for x. That works. What else could you do? If you got one of them fancy TI calculators, you can actually program in the quadratic, and you could just punch in the numbers to tell the calculator to calculate the quadratic for you. Okay. Desmos will plot like crazy, from what I've seen. Okay. In fact, I've seen people aggressively leaning into Desmos to do solves as opposed to dealing with any of the quadratics. Kind of, sort of? Is there another way? Sort of. You're just going to guess and check x values?
Well, after
Okay, after the quadratic formula or Desmos solves it for you, you're going to guess and check? I would argue it's already been solved for you. There's one more approach that you can go through and do, because it can simplify your solve a little bit. It can take it out of a quadratic and just into a square. We can go through and do an assumption. Whoops. We can assume x is much smaller than 0.02. What does that do for us? What is 0.02 minus a number that is much smaller than it? 0.02, which means that x can be eliminated from our expression. This can then change to x squared equals 0.02 times 10 to the negative 4.5. How do you solve for x? Take the square root of both sides and you now have an x value. That doesn't involve the quadratic. That doesn't involve plotting things. However, it does make an assumption. And what's the problem with assumptions? You get to make an ass out of you and me, right? So we got to be real careful with making that assumption. That's something you should double back and check. Okay, how do you double back and check? What was this assumption? That x was much smaller than 0.02. So what you would go back and do is take your x value. Did anybody actually solve for an x value? You all have calculators. You expect me to do squares in my heads? Right. If we run the assumption, we'll get an x value that I think actually works, but I'm not positive. 0.02 times 10 to the negative 4.5.
Why did I get it?
Yeah, you do.
Shouldn't it be maybe 4.75?
Did I drop the 7? Yep, I did. Apologies. For the record, this is why I don't like teaching this class. Drop numbers right and left. So what do we get for x? 5.86 10 to the negative 4. 96. Man, yet another case. 10 to the negative 4, and then you would double back and compare that to 0.02. I believe it's called the 5% rule. So you take this number, you divide it by your 0.02, multiply it by 100. Are you less than 5%? Yeah? Your assumption's valid and you're okay to use that. Okay? Did anybody actually solve it the long way through the quadratic? You're my Mr. Math whiz right now. Did you solve? Oh, come on. Okay, I think the assumption is going to work, and if the assumption works, what can we go through and do then? What did we say x was? We said x was a lot of things. Letter x, y, before y. What else did we say x was?
Increase or decrease in the concentration.
Cool. It was the increase or decrease in the concentration. Do I care? I would argue that one's absolutely valid, not the one I wanted. What did I say x was? What's that? Yeah, it's 5.96, assuming that all math, right? What was the question asking for? We did all of this work, but why? I want to know the concentration of H3O plus. What did I say X was? Yes, it was the increase or the decrease. It was the increase of what? H3O plus. So it could say it's plus X, or I could just say 5.96 is the concentration of H plus at equilibrium. That's exactly what I was solving for. So it's not that you're wrong, you're absolutely right. Okay? But what we're trying to do is find the useful thing for us. The useful thing here is that I wanted to know the concentration of H3O plus. So I would go back to my concentration of H3O plus at equilibrium. Okay? If we had a nice little table here, this is my magic answer right there. Since I said X was 5.96 times 10 to the negative 4, boom, that's now my concentration of H3O plus. Am I now done? No, why not?
Calculate pH.
There was a second question, and the second question was calculate the pH. How do you do that? Lies. How do you calculate pH? What is P? Some letter after M. It's after O. That was a joke. Calculate a pH, what do you have to do? The negative log of the H3O plus concentration. So all you have to do is take the negative log of this. What do you get when you take the negative log of that? You get a pH of 3.2. Is 3.2 acidic or basic? Acidic. Should it be acidic? Why yes? It's acetic acid. Okay? So we do have some internal checks to ensure that you didn't make a boneheaded mistake like myself in dealing with those numbers to make a big enough swap to swap your pH around. So that at least is internally consistent. Kind of make sense? So the ICE table just helps to organize our logical flow. It helps point out that we're looking at Q. It acknowledges that we're having a change. That change is going to navigate us to an equilibrium. That equilibrium we can then plug into our K expression, and now we can go through and start to solve for pieces. Make sense? Questions? What's that? Okay. So cool, new question. What is the concentration of H3O plus at equilibrium if 0.02 molar HCl reacts with water? Calculate the pH of the solution. We're going to resume recording on this one because I think you guys have struggled through this enough. And I appreciate everybody's efforts that went through and did this. Okay, I saw lots of ICE tables get set up, which is great. You'll respond less great in a second. But if we take 0.02 molar HCl, that's our 0.02. Okay, we start with 0 and 0. What happens? This goes down by x, this goes up by x, this goes up by x. We get 0.02 minus x, x, x. One thing that was a problem is people tripped up on that negative pKa, which means if you go through to calculate your Ka, that's going to be 10 to the negative pKa, which is going to mean 10 to the positive sixth. We could go through, set this up, x squared, 0.02 minus x. This is not one that the assumption is going to work for, okay, at all. We'll come back to that assumption statement in a second. Okay? When we go through and plug this all in, people that went through and got the quadratic and they solved it all out, they got two values for the x, which is standard. I think some crazy weird negative number, and 0.02. Did you screw up? No. I mean, it kind of is, yeah. I did kind of lead you into this. Okay. Let's go back. We didn't technically make an assumption, but let's go back to the first two lines of our ICE table. We start with 0 and 0, right? And as it changes, yes, my products are going to go up by x, my reactants are going to go down by x, and that's dictated based off of the size of our K. How big is our K? Large. Really, really, really large. So large, in fact, what happens? There's no reactant. If we go back and reflect back towards our strong acids, which HCl is, it's actually stated up in the question that it's a strong acid. What do strong acids do? They completely dissociate. Which means, what is the size of X going to be? 0.02. The HCl is going to completely dissociate, which means negative x, 0.02. Positive x, 0.02. H plus, 0.02. And so for those people being, well, why didn't you tell me that to begin with? Well, we need to trust that the ice table and all of those calculations work. Did they? Yeah. They end up spinning it around and showing us that if we have a pKa in this case, that's really, 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 really small, what happens? Everything completely dissociates. We're looking at effectively 100% conversion, which we said never happens. Real nervous. I just saw a secretary go that way. She's not supposed to go to that room. Sorry. It means that we're effectively getting 100% conversion. We don't need to do an ice table if we get 100% conversion. We only need to do an ice table if we don't. So if we're looking at strong acids, concentration of your H plus at equilibrium is the initial concentration of our strong acid. It completely converts across. I don't need to launch into an ice table. It's a perfect one-for-one match out. Kind of, sort of? Right. This is why it can be really critical to know what your strong acids are. So as soon as you see it, you go, whoop, done. I know what my H plus concentration is. I don't have to ice table. I can, but it's not necessary. The only time it's necessary to deal with an ice table is when I'm looking at a K value that's under 1. Okay, and even then, well, actually, under 1. Okay. The next part that we've got to deal with, because some people try to deal with an assumption, okay, is 0.02, what we solved for x, significantly smaller than 0.02? No, which means the assumption would have failed and the whole system falls apart with that assumption. Okay? When does the assumption hold? pKa's of I think it's right at 10 to the negative fourth. Okay? 10 to the negative fourth and smaller, you can absolutely run the assumptions. 10 to the negative fourth and larger, the assumption starts to fall apart. Okay? So is this a good thing or a bad thing? Bad thing? It's a bad thing because you spent 5 minutes working through something that you could have known right at the beginning, but I would argue it's a good thing because you don't have to do that work anymore.
So when it says a strong acid, it's
As soon as you see strong acid, boom, concentration completely moves out. Okay, the H plus is my initial concentration of whatever my starting acid was. Okay, how do I solve for my pH now? Same way I always solve for it, negative log of the H plus, so a negative log of 0.02. And I would get my pH. Kind of make sense? So while the ice table is a valuable tool to organize our flow, we do have to be aware of some of the magnitudes of our K values in those manipulations. Questions about that? Hi. So pH of the acid depends on the Ka and the concentration of the acid. Okay, so Ka or pKa's can be used to rank strengths of acids. We don't want to use pH or H plus to rank the strength of the acid because the pH is heavily dependent on concentration. Okay, the Ka and the pKa normalize that data and allow us to create rankings of strength a lot better. If we go through and shift to pH, the concentration is going to control a lot of that pH scale. Okay, the initial concentration that we start with. So it's dependent both on the pKa and the rest of the system. Kind of make sense? So I could get a 3.4 pH for acetic acid at 0.01 that is lower than the pH for HCl because the initial concentration was so different. Okay. Kind of make sense? So we got to be a little bit careful with how we manipulate our solutions and have to be kind of secondarily aware of those places. So what concentration of acetic acid would you need to make a solution as acidic, same pH, as a 0.1 molar HCl? What can we do to cheat? Go back, but we're not going to do that. All right? When we're talking about pH, it's the concentration of H+, but it's the concentration of H+ when? pH, by definition, is always at equilibrium. Okay? We don't get to test pH during the course of the reaction. It's already stabilized and finalized at your equilibrium. So this is one of the things that's both good and bad about our acids and base reactions. Their equilibrium attainment is so fast that as soon as we have a pH recording, the reaction's already done. Okay? We're already at that equilibrium state. So if we're now hitting a question, what's the concentration of acetic acid that you need to make a solution as acidic as a 0.1 molar HCl? Right? Well, when it says 0.1 molar HCl, what is that really telling us? Concentration? Concentration of what? Pineapples? H3O plus. The HCl immediately converts into our H3O plus. This is our 0.1 molar, H3O plus. The 0.1 molar H3O plus at what point? At our equilibrium. Okay? That's what I'm trying to target. Okay? And I'm concerned about the acetic acid solution. Okay? In this case, it becomes a little bit tricky to kind of manipulate things. Okay? We could go back and deal with structures, or we could realize that we have acetic acid. What is acetic acid going to do? It's going to react with water to do what? Okay, it's going to make the conjugate. I'm just going to write it as acetic because we're like, I don't know what that structure is. Plus what? H3O plus. If I'm being asked for the concentration of acetic acid that I need to make this solution, that's asking me about the initial concentration. So if I'm looking at an ice table again, I want to know that value. Okay? Initially, I'm going to have zeros for those. What's going to happen? That X value needs to go down, right? How much does it need to go down by? Okay? It needs to go down by some concentration, right? Because we're not at equilibrium. Okay? This creates a problem because we have a new variable. This new variable is going to get fixed in a second, and some people have already extrapolated out what this needs to be. What happens to the conjugate base acetic acid in this change? It goes up by that same value. We're picking Y because we already need that X, right? Okay, what happens to H3O plus? It's going to have to go up. If we look at the equilibrium concentration, okay, the equilibrium concentration, whoops, I don't need that X there, is going to be X minus Y. That's going to be problematic to go through and solve for. Okay, it's going to be a positive Y. Positive Y. We'd be like, well, if I try to solve this in my K expression, this isn't just one unknown. I've got two unknowns, and this is going to be a real big mess. Except we were given a little bit of information. What information were we given? We were given that what we're trying to target is an equilibrium concentration of H3O plus being 0.01, which means, whoops, we know this equals 0.01, which then means this equals 0.01, this equals 0.01, this equals 0.01. Gets a little bit tricky with that. We'll go here. 0.01, negative 0.01. Okay? Okay, how does that help us out? What does our K expression become? What are our products? 0.1? Oh, son of a horse.
You should have just made the 34 moles.
I hate my life. Of course, this is Monday too. You just had to wait till I asked for it at the very end, didn't you? 0.1 squared. Okay, what's our denominator? X minus 0.1. What would this need to equal? This gets a little bit tricky because it's not given to us here. That's our Ka, so we would actually have to be given the Ka information. 1.8 times 10 to the negative 5? I got a nod, yes, I think it's on the previous slide. But if I go backwards, I'm going to delete all this. All right, now what can I go through and do? All I got to do is solve for x. Kind of make sense?
So the only reason you knew the 1.8 times 10 to the negative 5 was because it was on the other slide?
Yeah, that has to be given to you to solve this. I guess for the sake of the recording, the 1.8 times 10 to the negative 5 has to be something that's given to you. You're not expected to memorize those K values or pull them out of thin air. Does that make sense? Now you set up your equation, solve for x, and you'd be done. Kind of feel like we've done a lot of calculator stuff, so I kind of don't want to solve for that. We good with that? Did you already solve for it?
Yeah.
Yeah, since you've got an answer. X.
5.5 times 10 to the power of 2. Oh, this, right?
10 to the power of 2?
Yeah. Yeah, I did that right.
Yeah, I question that. That's
Me too.
10 to the negative 2, maybe. Okay, we're going to erase that. You can deal with that mathematics later to go through and solve. Make sense? Ow. Knuckles. Hi. So which is more acidic, a 0.001 molar solution of nitric acid or a 1.5 molar solution of benzoic acid? What do you have to do? You're going to have to go through and calculate concentrations of H+. Okay? Officially, how many times do you have to do it? Once or twice? It's actually really only going to come out to be once that you need to run it for. Why? You can make the argument that twice, but I would argue you only need one ice table. Do you need an ice table for nitric acid? I asked the question, so.
The same concentrations.
They aren't the same concentration. Nitric acid is 0.001, the other one's 1.5. You don't need an ice table for nitric acid. Why not? It's going to fully dissociate. Why? Okay, it's very acidic. Okay, that's sort of okay. I'd like a little bit more than that. I heard a couple other people mumble it. It's a strong acid. Okay, how do you know it's a strong acid?
PK is extremely small.
Okay, the cheat you can lean on without having to have it memorized. You're given the pKa. You're looking at a pKa that's negative 1.4. So that is a very strong acid. If you go through and run your ice table, what you're going to find is the concentration of H+ for nitric acid is going to be 0.001 molar. It's going to come out to be exactly that. So what you would then have to go through and do is set it up for the benzoic acid. Depending on how many times you've run these particular types of questions, you might go through and start jumping to the very end of that ice table. I personally would never do that because you've already seen how much I can screw up the calculations. So I would write out all the gory detail behind it. For me personally, okay, drawing out that structure is going to be a bit nasty. So what I would do instead would be, say, HBA plus water gets me Ba minus plus my H3O plus. Technically, it's in equilibrium. I can look at my HBA as a 1.5. These are coming in as zeros for my initial. My change minus x plus x plus x. My equilibrium 1.5 minus x. That's a minus. Didn't look much better. X. Okay. Personally, I don't like seeing things as a pKa. But my Ka is going to be my Ba times my H plus. I wrote it as H plus, didn't I? Oh, cool. I did do a good job of writing it. I'm going to get x squared over 1.5 minus x. This is going to equal 10 to the negative 4.2. I'm going to run my assumption first, hope for the best. Okay. With a negative 4.2, I'm right on that threshold. I'm probably okay with that assumption. And I would go through and get my x value. Once I had that x value, I could now go through and compare that back to the 0.001. Did you solve for an x already? Is that a no? 9.73?
Times 10 to negative 3.
Okay. What was the concentration for nitric acid? I would argue 1 times 10 to the 1, 2, 3. 10 to the negative 3. Which number is the larger number? Which number is the larger number? Did I do that in my head wrong? Isn't the benzoic acid a bigger number? 9.73 times 10 to the negative 3 is larger than 1, isn't it? Okay, just checking. Okay, which means the benzoic acid at this point is more acidic. Kind of makes sense? Okay, so if you've got those strong acids memorized or you recognize the value of those pKa's, you can shortcut some of that work instead of having to duplicate it. Good? Okay. So what happens when an ionic compound dissolves in water? Okay, your ions dissociate into your positives and negatives. They get surrounded by the water molecules, and you create these large extended structures. Okay, this is officially known as a hydration sphere, right? But we typically write it out as the expressions that you guys have already seen. Your sodium chloride solid becomes sodium ion, aqueous, and chloride ion, aqueous. Right? Okay. If we pushed through to a solubility table, I'm going to assume you guys saw something like this in 151. Okay. Your textbook probably has something similar, but you could go through and manipulate and see what things were soluble versus insoluble. Okay. If they're insoluble, our assumption right out of the gate was they did not dissolve. If they were soluble, they dissolved completely, and we just kind of left it at that. Okay. Because we're 152, nothing is complete. Okay. If things are completely dissolving, the calculation, the number systems there aren't going to come out as anything particularly interesting or valuable for us to play with. So what we'll end up looking at as the slightly soluble or the insolubles. Those, we can now look at what's known as a solubility product. Okay, so let's pick one real quickly. If I took a look at just that magnesium and the fluoride, what we're saying is that if I mix magnesium ion and fluoride ion together, they would form magnesium fluoride. And if I wanted to get extra specific, which is what we're trying to do here, we're looking at them forming a solid, and these would be aqueous. That is typically how you would look at that chemical expression in a 151. If we mix a magnesium ion solution, a fluoride ion solution, ta-da, precipitate. Yay, chemical reaction has happened. Right? In this case, it would be what kind of chemical reaction? Bit harder because we removed the counter ions. This would be a double displacement, okay, or a double replacement, depending on how your Dr. Schneblin talked about it. Okay? When we move into 152, we care about K expressions. We're talking about these reactions going in reverse. Is the equation I've written up there going to be useful for our K expressions? what would we write out our K to be? Our magnesium fluoride over the concentrations of our magnesium ion and our fluoride ion. And then this expression gets a little bit wanky, janky, weird, okay? Because that magnesium fluoride is a solid, which means that gets factored over to the other side, and we end up with fractions right away. Does anybody like fractions?
No.
No. So instead, what we have decided to go through and do is we flip the equation on its head. And we would go through instead and say, I now have magnesium fluoride in its solid state. Some of that is going to dissolve into the ions. Our magnesium ion and our fluoride ion, again, with our aqueous. Okay? For the most part, it's going to heavily favor the reactants. Oops, erased a line to only see another line there. Okay? But now when I look at my K expression, I'm going to have magnesium ion, those are brackets, times the fluoride ion. Okay, and of course I picked one we got to be a little bit careful with. Why do we got to be a little careful? Ooh, sounded like a little rat. Okay, in the balanced equation, we've got 2 fluoride, which then means this comes in as the second power when we're looking at our K expression. Right? That was totally unintentional, but that's a really important observation that we need to nail down. Okay, so we have to be real careful. That coefficient is going to come into our K expression. Okay? This is now the K expression for looking at a solid dissolving. Okay? And if we look at what we're doing on the other end, we're multiplying, also known as a product, the individual ions. Since we're talking about solubility, we get the solubility product, because it's the product of the individual ions that made up that salt. Right? So our K expression is now KSP for solubility product, because you're talking about something dissolving. The solid doesn't factor into the equation because effectively its concentration is either 0 or some massive number, okay, massive unchanging number. So it disappears from the expression, and now what we've got is a K expression. What can we do with this K expression? The same thing we do with all K expressions, and we now go through and we solve for those individual ions. Okay, those individual ion concentrations, we would need to know K values, and all that fun mumbo-jumbo comes right back into it, and it's the exact same play that we've been making for everything else we've been doing. Okay? The subtle change is how we focus our directionality of the reaction. We don't look at the formation of the solid, we look at the dissolving of the solid. Okay? That just changes how our K is represented, and that becomes important because that's now a definition that we need to be aware of when we're dealing with our solubility products. Kind of, sort of? Okay. So it is a spectrum. You'll encounter things that are both more and less soluble depending on where you're at. Okay? And for different substances. So sodium chloride, super soluble, silver sulfide, or the calcium carbonate, less so. Okay? So depending on what you're concerned about and what you're studying, you may want varying pieces of information to be solved out of that system. The KSP, as we just defined, is our equilibrium constant. So if we go through and look at a whole list of formulas, all of those formulas, according to the previous table that we were at, they're insoluble. That's what we studied in 151. We just said they were insoluble. Now we're actually quantifying how insoluble they are. Well, if they're insoluble, how much product should we produce? Remember what our K expression is? Okay. We have the solid going to the aqueous species, right? If they're insoluble, do I get a lot of aqueous? No, I get very small concentrations of my aqueous. And if I now go through and run a solubility product and I multiply those small concentrations, what do I get for my K? When you multiply a small number by a small number, you get an even smaller number. So if we're looking at our K values, what you'll notice is that they are all really, 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 really tiny. Okay? The smaller the number, the less soluble that individual species is. Okay? So which compound with carbonate is the most soluble? That's what we need to go through and do. Oh, that's not too bad. Right out of the middles. Oh, I hate this table already. Why might I hate this table? You laughed, so I'm going to guess you have an idea. What's up? Yeah. If we're going to try and evaluate which one's more or less soluble, we just evaluated the magnitude of our K, and the smaller the number, the less soluble it was. So we would try and pick the top or the bottom of our table, except it's not organized based off of numbers. It's organized based off of, what is it organized by? I was going to say alphabet, but it's not the alphabet either.
Formula? Or the
P by name?
maybe.
It's by name.
That's kind of gay.
That's really weird. It was like, it's not even by name because you got lead in the middle of it, but or PB in the middle of it. Okay, but it's by alphabetic name for the individual elements. This is an annoying table. But to go through and answer this question, your most soluble is going to be the one with the largest KSP, so the least negative value. So we're looking at our negative 9s. I see a 6. I see there's negative 5. Didn't see it. We've got a negative 5. So the magnesium carbonate is going to be our most soluble. All right. Our least soluble is going to be the one with the largest negative number. You know what I mean by largest negative number?
Yes.
Okay. Good. We're looking at negative 13s. I see a 1.5,
8.
and an 8. We have to be careful on that one.
Oh, it's that one.
Because 8 starts to navigate closer to the 10 to the negative 12, right? So I think it needs to be the 1.5. Okay. Kind of, sort of? Cool. Thank you for paying attention.